This is the chapter 6 Freeman's machine, and we will solve together this tool problem. That is a machine problem because it's made to move, or the parts are made to move all together, but right now we are in this position. The question is, if we apply a force of 150 Newton on the handles, what is the force that is applied on the little cylinder there? Okay, so if the force of the cylinder are in this direction, it means that the force of the cylinder are in the other direction. But let's do one step at a time. The first thing I made is I split all the parts of this tool to make free body diagrams. And I will do all the free body diagram with you, and after that we will pick the free body diagram that will help us to solve one unknown at a time. Okay, so let's do this slowly. What we know first, there's two forces that we know. We know this 150 Newton there, and this one on the bottom, on the lower handle. It's Newton, both of them are Newton. Okay, let's look at this one on the top. We have pin connection, so CX, CY, and I will follow the X and Y X and Y axis when I don't have any idea of what are the direction of CX and CY. A, okay, at A, it's a pin connection, so we also have two unknown, AX and AY. But what we should do first is look at all the parts and see if there's two forces member. And if we look at AB, yes, there is two forces member. AB is a two forces member. It means that the force AB are aligned with the two pins, the pins at A and the pin at B. Now, what are the direction of the force? Is it a compression or a tension on this part? We are pushing on both handles, so we try to compress this bar. So it will be in this direction and these directions. Okay. Same magnitude, but opposite direction. Let's call that FAB. And FAB, but the same magnitude. So it means that A, what we have is the opposite force of this FAB. So this one is the force of the member AB on the lower, the upper angle. Okay, and we know the direction of AB. So if we want to write the direction of AB, let's write all the directions in green. What we know there is we know this dimension 70 and this dimension 30. Right? So this one triangle there is 70 on X and 30 on Y, and this one will be 30 square plus 70 square, and I take the square root. So this, we can find the angle if we want. Either you find theta, so how much is theta? Theta is the tan, the inverse tan of 30 divided by 70. So theta is equal to the inverse tan of 30 divided by 70 is 23.2. So it means that this angle there is also theta with the X. Okay, so that's very helpful because we have three unknowns, so technically we are able to solve with that. Oh no, we forget one thing. We forget one force. There is a contact at E. There is a contact with the cylinder. And the cylinder, we are pushing on the cylinder. Okay, we are compressing the cylinder. The cylinder is pushing on the blade here. Okay, so we have a force NE, and that's our final unknown. That's what we want to solve. Okay, so we have 1, 2, 3, 4 unknowns there. Okay, so we are done with the free body diagram. This one, we will add the dimension that we want a little bit later. Okay. This one, make it a bit bigger. So it's a little bigger. So on AB, on the member AB, we have one force, the same on both sides, but we don't have any force that we know. Let's look at this lower handle. At B, At B, this FAB is the same there. So we have the FAB also with still the same angle theta that we know. We found 23.2. Okay. At D, we have two unknown, dy and dx. Okay. I just put them in the positive direction on the x and y. And now, let's look at this little cylinder. We are pushing on this cylinder on both sides with the same magnitude. So it means that here, on the lower blade, we also have an E. At D, we have this dx, but in the opposite direction, and this dy in opposite direction. And at C, we have this cx and the cy in opposite directions. A little bit too much on this side, but you know what? We will not use that at all. So we say, let's just write what we know. On the upper handle, we have 4 unknown. Okay. We need to begin on a part where we have a force that is given. There is no choice. We need to have at least one information to solve an equation of equilibrium. So either the upper or either the lower. If we look at the lower, oops, I'm sorry. I don't know how to change that. And I'm back, sorry. So on the lower handle, how many unknowns do we have? 1, 2, 3. 3 unknown. Look like a good deal, right? And we have 1 unknown at A, at B, and 2 at D. So if we do the moment about the point D, there, the moment about D is equal to 0, we can solve for FAB, right? But we need more dimensions. So let's look at the dimension that we miss. We are missing the dimensions between D and B. That is 30 millimeters. B and D are on the same level. They are horizontal. So we don't need any vertical distance. And between the 150 and D, we need all these dimensions. We need the perpendicular distance to the force 150 Newton, because we need to find a moment. And that will be 30 plus 70 plus 30. So it's equal to 130 millimeter. So 30 plus 70 plus 30 to go up to D. So now we can solve the moment about D. So, oops, I was too fast. So sum of the moment about D is equal to 0. So what do we have at D? We have the 150 Newton times the distance, that's 130 millimeters, and you can keep everything in millimeters. This is the millimeters. This is the Newton, and it's rotating in a negative direction, so minus negative directions, trying to rotate clockwise. And the FAB, what we need is we need the vertical complement of FAB. We also have the horizontal complement, but the horizontal complement does not create any moment because it's aligned with the point D. So we need the FAB, and FAB is rotating in the positive direction counterclockwise. So plus the FAB, the vertical complement, so that the opposite to the angle theta, so sine theta, time the distance D, that is 30. So this is the millimeters, and this is the Newton, this FAB on x, and it's equal to 0. So we have FAB, that is equal to 150 times 130 divided by the sine of the angle, that is 23.2, times 30 millimeters. So FAB is equal to 150 times 130 divided by millimeters sine 23.2. Make sure to use millimeters everywhere. So it's 1650 Newton. See how much is that? That's a lot compared to, we multiply by 10 the force between the force on the handle and the force inside these two forces members. We found FAB. So now what we can do is FAB. We can write that FAB is a given force, is a known force. So we found FAB. So we mean that FAB, we know the magnitude, we know the magnitude of this one, that's the same, and we know the magnitude of this one. We know the magnitude of FAB. So on this upper handle, it's not 3, 4 unknowns, it's 3 unknown. Here we go. Let's look at the upper handle. We have the 150 that we know, the FAB that we know, it's, how much is that? 1650 Newton. We know the angle theta, and what we don't know, there's a lot of information on that. We don't know the NE and Cx and Cy. So we have 2 unknown at C. So if we do the moment about C, we will be able to solve for NE because the 2 other forces are known. I want to do it blue. I don't know why I like it. That's a blue force, not a purple force. Okay, because we will do the moment about the point C, we need all the dimension from C. Okay, so we have the direction. We need the minimal distance between the point C and this 150 Newton force. So let's go on the top there. So this is 30 plus 70 plus 30 again. So 30 plus 70 plus 30. So it's 130 millimeter. We need the dimensions between A and C. So between A and C, that's 70 plus 30. So it's 100 millimeter. So this is this one plus this one. So this is 100 millimeter. Okay, and we need the dimension between C and NE. So between C and NE is 30 millimeters. Okay, and the point A and the point C are horizontal. It's a line. So there's no gap between the vertical position at the point C and the point A. So now that we have all our dimensions, all our forces, we can solve MC. Let's do that. Let's make it a little bit bigger. And I will move it there. Okay, so let's do sum of the moment about C is equal to 0 on the upper handle. This 100 Newton is turning in the positive direction. So we have 150 Newton times the distance from C, that is 130 millimeters. We have the FAB, and the FAB, we need to split the FAB on 2 forces, so on X and Y, but the force that we want is the force on Y, so that's the sine theta. And FAB is rotating in the negative directions, clockwise. So minus FAB sine theta, so that's the Y complement of FAB, times this distance, that is 100. And E is rotating in the positive direction, so plus NE times the distance from C, that is 30. It's equal to 0. Cx, Cy, they are on the point C, so we don't need them. Okay, so we have 150 times 130, so that's 1950 minus FAB. We found FAB, that was 1650 sine the 23.2 degrees times 100, and this is equal to minus 30 and time NE. So let's find how much is that. 19,500 minus 1,650 times 100 and times sine 23.2. Okay, so that's minus 45,500. It's equal to minus 30 NE. So we found that NE is equal to, and if you find a negative answer there, you made a mistake somewhere. Or maybe you turn your force in the wrong directions. Okay, but it's a normal force, so it can only be a force that is pushing on the surface. Normal force cannot pull on the surface. Okay, so let's use that. Minus divided by 30. It's 1,517 Newton. Let's square that. Here we go. So, in conclusions, what we found is if we apply a force of 150 Newton on the handles, we will push. Okay, and now my body is a little cylinder. We will apply a normal force of 1,517 Newton on the cylinder. So we multiply by 10 the force on the cylinder. That's why, so from 150 to 1,500. That's why we use those tools to cut some metal wire or something like that. Okay, and freebase diagrams, try to take your time to do all your freebase diagrams and identify the parts that are two forces member. So the two forces member were this one. Identify the parts where we have only three unknown. So first we identify the two forces member. Second, we find the force FAB. We report in the two forces member and there. And third, we did the moment about C with the upper handle. So we solved two equations of moment, and we needed like 3-4 freebase diagrams if we include this one. This part, C, D, E, we could have used it, but I think this way was the fastest way. So that's it for this example. See you for the next one. Bye bye.